Hello student, we'll see integrator circuit. Integrator circuit is categorized as active integrator and passive integrator. When I say passive integrator, that means it is combination of only capacitor and a resistor. Whereas I say active integrator, that is C and R is combination is applied to op amp. So this one is ideal active integrator. The feedback resistor is get replaced with this feedback capacitor. So we'll see analysis of it. Here at this point V2, I'll apply KCL. The KCL says that sum of incoming current is equal to sum of outgoing current. Here incoming current is equal to I1 and the outgoing currents are IB and IF. So I1 is equal to IF plus IB. We know that the ideal op amp having infinite input impedance. So because of that, the input current of terminal is equal to 0. So this IB will be 0. So you'll get equation I1 is equal to IF. We know this I1 current, the current flow is due to potential difference at 2 points divided by resistance fixed by that path. So here I1 is due to potential difference of VEN minus V2 divided by total resistance offered by this path is R1. But we know the voltage across the capacitor and the current across this capacitor is equal to, the relation is equal to IC is equal to C into dVc by dt. This dVc is nothing but voltage drop across this capacitor, and the IC which is equal to IF itself. So I can substitute this I1 is equal to V in minus V2 divided by R1, and Vc is nothing but voltage drop across a capacitor, which is equal to V2 minus V0. Now I'll substitute these two values into above equation. So I'll get I1, instead of I1 I can substitute V in minus V2 divided by R1 is equal to, instead of IF is equal to IC, which is nothing but C into d by dt V2 minus V0. This V1 is connected to the ground. So because of virtual network connection, the V2 will be virtually ground. So this V2 will get cancelled. So you'll get, after simplification, the V out will equal to minus 1 upon R1 CF integration V in limit 0 to t plus constant. This is the integrator output. If I'll give square wave to the input, I'll get triangular wave at the output, because if I say V in is equal to something V, or I say A value, the amplitude is equal to A. Now the integration will be minus AT. With the plus amplitude or plus voltage will goes to negative. This negative sign indicates there is 180-degree phase shift between input and output. If I'll give sine wave at the input, I'll get this cosine waveform, because we know the integration of this sine is nothing but minus cos omega t. So I'll get with this shift, omega shift, at the output side, you get cosine waveform. But there is a problems are associated with this ideal integrator. What are the problems? The capacitive reactance will be infinite. We know in ideal integrator, the CF is connected in feedback path, which decide the gain of this inverting amplifier. We are using inverting amplifier, then the gain is equal to minus RF upon R1. But here this RF is nothing but XF, which is the reactance of this capacitor. In the absence of any input signal, the capacitive reactance will be infinite. If this infinite, what will be the gain? The gain will be also infinite. Now, it will amplify any input signal, any input offset voltage which is present at the input of op-amp. Obviously, the error voltage will comes, and this is nothing but one of the problem. The other problem is the integrator output is ramp up or down. Its output is to ramp or ramp down. The bias current of op-amp can be charged or discharged this capacitor. The capacitor is connected to the feedback network. This bias current will charge and discharge the capacitor, which forcefully ramp up or ramp down to integrator. Due to these two problems, the output voltage is like ramp up or ramp down to very high gain. The next problem is the ideal integrator is that the gain of the amplifier, which is at infinite, it goes on decreasing with increasing frequency. Hence, it unable to integrate high frequency input signal. So to rectify this drawbacks or some negative values, the practical integrator is get modified. The first modification is done for the bias current, which ramp up or ramp down the output of integrator. To rectify this, they introduce this RCOM resistor, which is connected to non-inverting terminal, which is equal to R1 parallel RF value. And this used to reduce errors due to this bias current. Next introduction of this RF resistors is in parallel with capacitor. Due to this inclusion of resistors RF across the CF, the low frequency gain does not becomes infinite. It restricts the value of minus RF upon RN. The value of this RF will keep as high. So it does not alter the output. At high frequency, XCF is very small, hence in shunt with this RF and high frequency gain of integrator will be low. So in practical integrator, they introduce this RF resistors in parallel with CF and this RCOM resistor to reduce this bias current. Thank you, student.